At the heart of HDM4 lies the Life Cycle Analysis Loop, a dynamic simulation that models the performance and cost-effectiveness of road management strategies over time. The loop begins with the start of analysis, initializing all parameters for the selected project duration. The first step in the loop is road deterioration, where the condition of the pavement is predicted based on traffic, climate, and structural properties. This reflects real-world aging and wear of the road surface. Next is road user effects. HDM4 estimates vehicle operating costs, travel time, and accident rates, all influenced by the road's condition. These effects help measure the impact on road users. Following that, we evaluate the work's effects. This step simulates how maintenance and rehabilitation activities improve road condition and influence performance going forward. Then, social and environmental effects are considered. This includes impacts such as emissions, energy consumption, and other externalities, providing a broader understanding of a project's implications. With all these components, HDM4 performs the economic analysis. It calculates key indicators like net present value, internal rate of return, and benefit-cost ratio, comparing alternatives against a base case. Finally, the model returns to the start of the loop, progressing to the next year in the analysis period, and repeats the cycle until the full life cycle is simulated. This continuous loop allows HDM4 to provide a realistic, long-term view of how roads behave, how treatments perform, and what strategies deliver the best value. Before HDM4 begins its life cycle simulation, it requires a comprehensive set of input parameters that define the road environment, traffic behavior, and cost structure. We begin by defining the vehicle types using the road, such as cars, trucks, buses, and two-wheelers. For each type, we specify the traffic volume, the expected annual growth rate, and traffic loading in terms of axle loads, which directly impact pavement deterioration. Next, we define key physical parameters of the environment, including terrain type, whether flat, rolling, or mountainous, and precipitation levels, both of which significantly influence road wear and maintenance needs. We also input road geometry details such as lane width, shoulder width, and alignment, along with pavement characteristics, including layer thickness, material properties, and current condition. To assess economic impacts, unit costs are provided for construction, maintenance, vehicle operation, and user time. Together, these inputs create a comprehensive profile of the road project and its operating environment. With all data defined, HDM4 proceeds to the start of the analysis loop, initializing the simulation and beginning its year-by-year evaluation of road deterioration, user effects, and economic performance over the full analysis period. This structured input phase is crucial, as accurate and complete data ensures meaningful and reliable results from the HDM4 model. In HDM4, pavement deterioration modeling begins with a specific set of input parameters that describe the existing condition and structure of the pavement. These include the pavement type, such as flexible, rigid, or gravel surfaces, and its strength, which defines how well it can withstand traffic and environmental stress. We also enter the age of the pavement, its current condition, and the equivalent single-axle loads, SL, it has been subjected to, representing the cumulative traffic impact. With these inputs, the model runs the road deterioration simulation, predicting how the pavement will age and degrade over time, based on traffic loads, climate, and structural properties. The outputs of this model provide a detailed picture of pavement distress. These include cracking, indicating surface or structural failures; raveling, where the pavement material breaks away from the surface; potholes, as a result of progressive cracking and material loss; rut depth, caused by repeated wheel loads; faulting, typically seen in rigid pavements at joints; gravel thickness, which diminishes over time on unsealed roads; and roughness, a key indicator of ride quality and user comfort. These outputs help road engineers understand the timeline and nature of pavement degradation, enabling informed decisions about maintenance timing, treatment selection, and budget allocation. Another critical part of the HDM4 system is the road user effects model, which quantifies how road conditions affect vehicle operating costs, travel time, and safety. The model begins with a set of important inputs. We provide details on road geometry, such as gradient, curvature, and lane width, along with the current roughness of the road surface. Next, we input vehicle speeds, vehicle types, including light vehicles, trucks, and buses, and congestion parameters, which reflect traffic flow and density. To support economic analysis, unit costs for fuel, tires, parts, and labor are also specified. Based on these inputs, the road user effects model simulates how road condition and traffic levels affect user experience and cost. The model outputs a range of detailed results, including fuel costs, reflecting how rough or steep roads increase fuel consumption; lubricant costs, which rise with engine wear under poor conditions; tire costs, due to faster wear on uneven or rough surfaces; maintenance costs, driven by vehicle damage from poor road quality; capital costs, linked to depreciation and reduced vehicle life; travel speed and travel time, both directly influenced by road quality and congestion; road user costs, which combine all these operating and time-related expenses; and finally, road accident costs, accounting for safety impacts under different road and traffic conditions. This model is essential in understanding how infrastructure affects not just public budgets, but also daily user costs and safety, helping policymakers justify investments that benefit both the system and its users. In HDM4, the works effects model plays a key role in simulating how road maintenance and improvement activities influence pavement condition, geometry, and cost. The process begins with a set of input parameters, specifically, the roadworks standards and strategies defined for each section. These may include treatments like resurfacing, overlay, reconstruction, shoulder improvements, or geometric upgrades. Once the strategies are applied, the works effects model evaluates their impact on the pavement. The outputs of this model include two primary results. First, it resets the road condition and geometry, reflecting the improvements achieved through the works. This could mean smoother surfaces, reduced roughness, restored pavement strength, or modified alignment. Second, it generates detailed works quantities and costs, which include materials, labor, equipment, and unit costs, helping planners estimate the total financial requirements for implementation. These effects are then fed back into the life cycle analysis loop, allowing HDM4 to assess how these interventions affect long-term performance, user benefits, and economic outcomes. By accurately simulating the results of maintenance and construction activities, the works effects model ensures that decision-makers can evaluate not only what treatments to apply, but also when and where they deliver the best value. In HDM4, road infrastructure projects are not only evaluated for their technical and economic outcomes but also for their broader social and environmental impacts. The social and environmental effects model begins with key inputs such as road geometry and surface texture, which affect vehicle energy use and emissions, and vehicle characteristics, including engine type, fuel consumption rates, and emission profiles. Using this information, the model simulates how road condition and vehicle performance contribute to environmental impacts. The outputs of this model include the levels of emissions, such as carbon dioxide, particulate matter, and other pollutants, as well as the amount of energy used during vehicle operation across different alternatives. These results help planners understand the environmental trade-offs of various strategies and support more sustainable decision-making in road infrastructure projects. By incorporating environmental metrics into the analysis, HDM4 promotes a more holistic approach to transport planning, one that considers not just cost and performance, but also the long-term impact on people and the planet. At the core of HDM4's decision-making capability is its economic analysis model, which evaluates the overall value and return on investment for each road project alternative. This model integrates several types of input data, including agency costs, such as construction, maintenance, and rehabilitation expenses; road user costs, including vehicle operating costs, travel time, and accident-related losses; and exogenous costs and benefits, such as environmental impacts or broader economic effects not directly borne by the road agency or users. With these inputs, the model performs a comprehensive evaluation of each alternative using discounted cash flow techniques. The outputs of the economic analysis model include total costs by component, allowing for a breakdown of where the investment is being allocated and which components drive the most cost, and critical performance indicators such as net present value, NPV, internal rate of return, IRR, and benefit cost ratio, calculated for each section or for the entire project, depending on the analysis method used. These indicators help identify which alternative delivers the highest return and ensures that public funds are invested where they yield the greatest impact. The economic analysis model provides the final layer of insight, enabling planners, policymakers, and engineers to make informed, transparent, and economically sound infrastructure decisions. HDM4 generates a wide range of analytical results, but at its core, it produces three main types of outputs that directly support decision-making in road planning and management. The first is economic efficiency indicators. These include key metrics such as net present value, NPV, internal rate of return, IRR, and benefit cost ratio. These indicators help evaluate the cost-effectiveness of different project alternatives, guiding investment decisions based on economic return. The second output is the multi-year works program. Based on technical and economic analysis, HDM4 recommends a schedule of maintenance and improvement activities over a defined planning horizon. This helps agencies allocate budgets efficiently and prioritize interventions year by year. The third is strategic road maintenance and development plans. These long-term plans are built from network-level analysis, enabling governments and agencies to set policy directions, assess funding needs, and plan infrastructure development in alignment with broader transport goals. Together, these three output types, economic indicators, programmed actions, and strategic plans, make HDM4 a comprehensive decision support tool for sustainable and cost-effective road network management.